So, hello everyone. In this lecture, we will discuss about the quantum efficiency. So, before going to this quantum efficiency, first we have to understand this nt is equal to n0 e to the power minus t slash tau. So what is tau? Tau is the carrier lifetime. So, in the semiconductor, there are two types of carrier, electron and hole, and this tau represents the lifetime of this electron or hole. And n0 is the initial excess electron density and n is the excess carrier density after time t. So this basic formula is used for calculating the value of excess carrier density. Now in LED structure we have seen the light is emitted. Here we have to calculate the quantum efficiency, and the quantum efficiency depends on the emitted photons. And emitted photons, how we will get these emitted photon? When this electron on hole recombine, then the energy is radiated in the form of photons or in the form of heat. So when the energy is in the form of emitted photon, then that is termed as a radiative recombination rate. And when electron and hole recombine and the energy is emitted in the form of heat, then that is non-radiative recombination rate. So in order to determine the bulk recombination rate in the LED, the total recombination rate is given by radiative recombination rate, that is output in form of photons, and non-radiative output in the form of energy liberated in the form of heat, that is non-radiative recombination rate. So we have to consider these two recombination rate to calculate the total recombination rate, and it is given by the minus dn by dt is equal to n divided by tau. N is the electron density, carrier density, and this is the lifetime. So now radiative recombination rate is given by 1 by tau r. This is the lifetime of radiative, and this is non-radiative uh, tau. Here we have seen non-radiative recombination rate. So those electrons, this is the lifetime of those electrons and holes which recombine and radiate energy in the form of heat. So here two types of recombination rates RR and RNR is defined. When we apply external current density having magnitude of J, then the rate equation of the electron hole recombination is given by J by QD minus N by tau. Here J is the current density, Q is the charge, and D is the thickness of recombination region. In LED, we have seen the active region is basically recombination region. Active region represents the recombination region where these all phenomena are going on. In case of equilibrium, this factor, the ratio of this is 0. So when we rearrange this, we will get the formula of electron density, that is n is equal to j tau qd. Now this is the base formula. Now next we have to calculate the internal quantum efficiency. So what do you mean by internal quantum efficiency? So internal quantum efficiency is given by the fraction of electron hole pairs that combine radiatively. It means due to recombination of electron and hole pair, which is giving optical power. So in this case, we are considering only the radiative power. So this is given by RR, R radiative, ratio of RR divided by RR plus NR. So R is recombination rate of only radiative carriers, and this is divided by the total recombination rate. So when we will calculate, we will get the final value of this. Here, this represents the internal quantum efficiency. So basically what we can say, internal quantum efficiency can be given by the ratio of number of photons generated and total number of electron hole pair. Suppose this is our LED and this is our reactive region. This is the reactive region where the recombination is taking place. So total recombination, so internal quantum efficiency is given by the number of photons generated divided by total electron hole pair recombination.